Okay, so we're going to talk about a couple definitions here. And the first one we're going to talk about is something called humidity ratio. Now, this is not what you have thought about when you think about humidity. This is not the same thing, okay? We can also use the word specific humidity. And we will. Okay, I want you to be able to use either humidity ratio or specific humidity interchangeably. Okay, and we're going to label that with a omega. Omega is going to be the mass of the vapor all over the mass of the air. So this is going to be the mass of the water vapor. And this here is going to be the mass of the dry air. Okay, now we can go and measure that. If in this room, if I could figure out what is the mass of the water vapor and what is the mass of the dry air, and I could take that ratio, I have the humidity ratio. And so the units here are going to be kilograms of vapor over kilograms of air. Now you have to think, the units don't really cancel because we're having, even though they're the same kilograms, one is of vapor and one is of air. So that does change things. It's not a unitless idea, because one of the top is going to be vapor, the bottom is going to be dry air. It could be pounds, pounds mass. In fact, in some areas, and some of you architectural engineers, if you deal with the HVAC company, you might hear this talk about grains, okay? In some studies, in some, I don't know, what do you want to call it, some industry standards, they use grains, and 7,000 grains is equal to 1 pound. Okay, and so there's a conversion there. They use just grains, and the reason why they use it, and I'll explain it a little bit later, is because the humidity ratios can be very, very, very small, decimal numbers into the hundredths and thousandth place that we're dealing with. So that's why we sometimes they convert it to this grains idea. Okay, but we look back at this humidity ratio and we say, man, it is very difficult to measure the mass of water vapor in air and the mass of just the dry air. So is there another way to do this? And so let's look at that. Let's say, well, omega is equal to the mass of the vapor all over the mass of the air. And they're both ideal gases, right? So let's see if we can say, well, that's equal to the partial pressure of the water vapor times the volume of that water vapor all over, let's do R, all over the molecular weight of the vapor times T. We take that all over the partial pressure of the air times the volume of the air all over the R bar over the molecular weight of the air times the temperature T. Okay, and we follow that Dalton model and we say, well, in the Dalton model, the volume of each component is the same as the whole, and the temperature of each component is the same as a whole. And also the R bar, which is going to be the universal gas constant, is going to be the same in all this nonsense. And so we end up with this. This is going to be the molecular weight of the vapor times the partial pressure of the vapor all over the molecular weight of the air times the partial pressure of the air. Okay. Now the molecular weight of the vapor and the molecular weight of the air, they never change. This is an unchanging idea. These are constants, and so what I can do is I can multiply those, or divide those actually, and I can get 0.622, okay, times the partial pressure of the vapor all over the partial pressure of the air. Now pressures are something that I can analyze a little bit easier. I can measure those a little bit easier with probes, sensors, things of that nature. And so this equation is a little bit more useful. In fact, let's make it a little bit more useful. I know the pressure is equal to the pressure of the air plus the pressure of the vapor. So PA is going to be equal to pressure minus partial pressure of the vapor. And that gives us in our final form that omega, which is equal to mass of the vapor all over mass of the air, is also equal to 0.622 times the partial pressure of the water vapor over the pressure total minus the partial pressure of the water vapor. And so these are the things that we need to know for a definition of what humidity ratio is. Now, humidity ratio is very important. As long as water is not condensing in our air, humidity ratio is going to remain constant. I'm going to write that down because it's important to say. As long as water vapor is not condensing, we're basically changing state. Okay, condensing means it's turning from a vapor to a liquid. The humidity ratio of a mixture will remain constant. Okay, that's not exactly true. Okay, that's true there, but there's one other thing that we have to say. One other thing that we have to say, and that is, as long as we're not adding any more vapor to the air. So you could have a humidifier humidifying the air. So we have to say here, as long as water vapor is not condensing, I should say here, or being added, the humidity ratio of a mixture will remain constant. Okay, so what we can have here is, it's the mass of the vapor over the mass of the air. Of course, if that vapor changes to a liquid, there's going to be less vapor, and so that humidity ratio is going to decrease. If I have a humidifier in this room and I'm adding water vapor into the air, now that humidity ratio is going to increase. Okay, but if either of those things are not happening, dehumidification or condensing of water vapor, or humidification, adding of water vapor, omega remains constant, and we have to keep track of that. That's an important thing for us to monitor or pay attention to in our problems. Okay. Now this is different than what you may have heard of. Is may have heard of something called relative humidity. Okay, relative humidity. And we're going to call relative humidity, we're going to call that phi, or we're going to just say RH for short. Okay. Relative humidity is what a meteorologist might say on a newscast, relative humidity. And we say relative humidity is equal to the mole fraction of the vapor all over the mole fraction of the vapor at saturation. Okay, so we're looking at the current mole fraction of the water vapor to the maximum allowed. Okay, so this is basically the current mole fraction. So this is here is going to be the maximum allowed. Now, mole fractions are also not fun to remember and have to work with. So there's another way we can use this equation. If we take relative humidity, which is YV, or mole fraction of the vapor over mole fraction of the vapor at saturation, and we take this times 1. We take it like times 1 like this, pressure over pressure. What happens? Now we have a partial pressure of the water vapor all over partial pressure of saturation, Okay, so we now turn it to partial pressures. And again, pressures are easier for us to remember. So this is how I am going to remember relative humidity instead of looking at mole fraction. But you need to know where it comes from. The official definition is mole fraction. The useful definition is what I have here in this box. Let's look at our TV diagram. Okay, so here's a TV diagram. The one we just showed earlier in the last video. I have two pressures. Here is going to be my partial pressure of the water vapor, and this is going to be the partial pressure of saturation. We are comparing between these two dots. We are comparing where we are to where saturation is. Now, this here is going to be the temperature of the mixture. Now, let me ask you a question. As the temperature drops, is our relative humidity going to go up or go down? This is not a quiz question, but I would, if it were in class, I would ask you this. As the temperature drops, would our relative humidity go up or go down? Think of that in your head. You have an answer. Okay. Here's the correct answer. It would go up. Now, why would it go up? It would go up because as the temperature of the mixture goes down, I did the wrong thing there. As the temperature goes down to this red line, look what's happening. The partial pressure of the water vapor is going to be nearer to the saturation pressure. Okay? Now the saturation pressure has dropped to this line. They're getting closer together, and so that ratio is going to give us a number closer to 1 until that temperature would drop all the way down till where it would meet here. And if it got there, now the partial pressure of the water vapor and the saturation pressure are the same. You would have saturated air and you would have 100% relative humidity, which is exactly what we're talking about, that saturated air. Remember, air is like a sponge. Okay, now, if relative humidity is low, that means that the air can accept a lot more water vapor in it. So if you have 10% relative humidity outside, you're like, wow, that air can accept a lot more water vapor. Okay, if it's very high, if you have 98% or 95% relative humidity, that air cannot accept a lot more water vapor. Okay, now let's just say you're going for a run. Okay, you're going for a run. It's a nice day outside. You decide to go for a run. Which would you rather go for a run in? Would you rather go for a run in 95% humidity or 15% humidity? Well, probably 15% humidity. And the reason is because your body is creating sweat. That sweat is coming off of your skin surfaces. If me is beat up on the top of my head. And then that sweat is going to evaporate and want to evaporate into the air. Okay? When that evaporates into the air, it cools you down. It gives you a feeling of coolness. Now, if the air is already very saturated, your body can't get rid of that sweat very easily, and it's just a muggy mess. Your shirt is just sticky, and you have sweat in places we don't want to talk about on this lecture. Okay, sweat works for you. That's why sometimes we use misters, spray misters, to kind of get that coolness, because what happens is the air will have to evaporates that water off of us, and it gives our body can give out heat to evaporate that water vapor and put it into the surroundings, and that cools us down. Okay, so we want to have that mist or that body sweat that's on there. Sweat is good for us. Okay, so we want to have those things, but it's not when it's just super muggy outside. So my wife was going to take a run the other morning, and it was a very low temperature outside. It was like 70 to 75 degrees, and she said the relative humidity is 100% or near 100%. Well, if it's cool outside, but then she would just feel like, oh, I'm just getting really, just couldn't get rid of that sweat. It would just make it a miserable experience. Okay. Okay, that's what we're talking about here. So the one question that you ask yourself is, now, okay, it's very muggy outside. It's 95% relative humidity. I'm sweating. I'm going to fan myself. Is that going to help me? Well, that's convection. When I fan myself, I am convecting. I'm moving air over my body. I'm going to feel cool. But I still have that the sweat is still wanting to try to evaporate into the surroundings. And now what I'm doing is I'm creating work. My body is now working, which is probably going to produce more sweat. And so the question is, is it doing anything for me, or is it just make me temporarily feel better? Okay. Last thing I'm going to talk about here before I move on, I'll talk about humidifiers. Okay, let's talk about the winter time now. Winter air, cold air, is very dry air, very dry air. So when we had children, Jonah and Lila, we had to figure out what kind of humidifier to put in the room. Okay, humidifier is ways to turn up that relative humidity. We actually want to be around a 45% relative humidity. That's when we feel really nice there. Want to make sure our skin is hydrated and things of that nature. So the question was, what kind of humidifier do you want to have in your house? Do you want to have a warm mist humidifier or a cool mist humidifier? And so if you go to a store, you'll see warm mist humidifiers are they actually heat up the water, turn it into steam, and put steam into the air. Cool mist humidifiers use ultrasonics or something like that to take little. They atomize water and put water particles, small water particles, into the air. And you look at this, and the cool mist humidifiers are recommended for kids because they won't burn themselves. All right. Now, which one did I buy? I bought a warm mist humidifier, and the reason why is simple. When you plug a warm mist humidifier in, you're probably in a cold environment. Maybe it's 30 degrees outside, and you're wanting to be in a room, and you want it to be nice and comfortable. Okay, the warm mist humidifier, when that's plugged in, that's putting steam into the room. It's actually helping the temperature of the room go up. You are adding moisture to the room and temperature to the room all at the same time. So they're kind of helping itself. Both of them are helping the cause. A cool mist humidifier, what's it doing? Well, it's just like what you're doing when you're spraying in the summertime, when you're spraying mist around yourself to cool yourself down. That cool mist will go up into the room. What will happen is now that warm air from the room is going to have to come and take the water and evaporate that water and turn it into water vapor. It's going to take energy from the air, actually cooling the air down in the room. Okay, so a cool mist humidifier will cool the air down in the room, and so you'll have to run the heater a little bit more in your house, a natural gas or electrical heater that you have in your house. Now, this is a minuscule amount of energy difference. I would like for somebody to actually, I tell you what, you want to have some alternative assignment. Calculate how much money I'm saving with a reasonable power consumption if I ran a cool mist humidifier and a warm mist humidifier for 24 hours and I want to keep my room at 75 degrees Fahrenheit. Find out how much money I'm saving. I bet I've saved literally 35 cents in the 9 years I had this, but because you might say, well, the cool mist humidifier takes less energy than the warm mist. I don't know, but thermodynamically, it's a great story to tell so that we can get the idea of relative humidity and how that works. I encourage you right now just to pull out your phone and to figure out what is the relative humidity in the area that you're living at. So let me just try here. Okay, Google, what is the relative humidity in Manhattan, Kansas? That didn't work. What is the relative humidity in Manhattan, Kansas? 77% right now. So we are pretty, it's up there a little bit, feel a little muggy when we go outside tonight. Okay, that's where we'll end this lecture portion.